All right. Today will be common logs and natural logs. We'll do more with that and with exponents. There'll be some review. Let's start with this. So write that down and start thinking through the process of what you would need to do to simplify. Notice it's simplify, not solve. The way we know we can't solve for this, I'm not going to get x equals at the end, is there's no equal sign. With no equal sign, you're never solving. You're just simplifying. So being careful when you're doing work as well, that if it says simplify, don't accidentally try to solve for something. But you got a whole bunch of fractions going on, so then thoughts should be popping up about what should I do when I know that there's fractions, how do I add and subtract fractions, and go on from there. So take a few minutes, start working on that while I get the attendance done.
Do you have a pencil?
Somewhat, yeah. So the idea of where to start is always a question when dealing with something like this. So when thinking about where to start, it's looking and saying, well, I've got fractions going on, there's just a lot going on. Best option, I said, is take this, rewrite it, and then see, is there a way, or is there something else I can do to simplify that to start with? So there I have two fractions. They have different denominators. In order to add and subtract, we have to be we got to be on the same scale. To add and subtract fractions, you got to be on the same scale, which means same denominator. Right now, the denominators are 16 and x. So I'm always trying to figure out, like, well, how do I get those to be the same thing? This is where we multiply by 1. So I'm going to multiply each of those by 1. So that way, when I multiply by 1, it doesn't change the value, it just changes how it looks. So one of them has 16 in the denominator, the other one has x in the denominator, which means my common denominator will be 16x. It'll be something over 16x and something over 16x. That'll be my common denominator. So to get that, I need to multiply the first equation by x over x, which is 1. X over x is 1. Multiplying by 1 is the multiplicative identity. It does not change anything, just how it looks. So that would then be x times x in the numerator, x times 16 in the denominator, so this will be x squared. That's x times x. Second one over here, I need this to be 16x. It's currently x, so my number 1 over here needs to be 16 over 16. Again, 16 over 16 is 1, and that's going to give me 16x in the denominator. So 1 times 16, well, that's 16. All right, so that's my numerator. Oh, but wait, I can now pull them together into one equation. X squared minus 16 divided by 16x. All right, so that's my numerator. I'm going to kind of put a pin in that, let that ready to sit. Now I'm going to look at the denominator and say, all right, let's do the same thing there. Rewrite the equation, 1 minus 4 over x. I'm like, all right, well, what do I have going on? Well, I've got this 1, which is just a number. It's not a fraction. Can I make it into a fraction? Yes. How would I make it into a fraction? It's 1 over 1. 1 over 1 is 1. So I can just write it like that. So now I'm looking and saying, all right, this is 1 as my denominator, x as my denominator. So my multiplying, I need to multiply this. Well, technically I'm just multiplying it by 1. This one I'm going to multiply by x over x, which is also 1. So I'll have x over x minus 4 over x. Common denominators, x minus 4 over x. All right. Remember when we add and subtract fractions too, once the denominators are the same, I just combine the numerator operations. The denominator stays the same. 16x, 16x, 16x. We're just about fractions. So now what I have is I have my numerator, which we did up here, which will be x squared minus 16 over 16x, all over my denominator, which is x minus 4 over x. And I am very intentionally making this a big fraction bar. So we can see that it's a fraction divided by a fraction. Now, dividing by a fraction. If that's not a phrase that automatically triggers your brain to think of a phrase, then this is a phrase you should write down and, I don't know, memorize it, or at least make sure it's on your note card. Dividing by a fraction is the same as multiplying by the reciprocal. So again, if that phrase did not pop into your head, then you're writing it down now. Dividing by a fraction is the same as multiplying by its reciprocal. So dividing by a fraction is the same as multiplying by its reciprocal. So here, I am dividing, that's what the fraction bar means. I'm dividing by a fraction. There's my fraction. Dividing by a fraction is the same as multiplying, so times its reciprocal. So I take whatever I'm dividing by and write its reciprocal. Reciprocal is a fancy word for flipping it over. So then this will equal x times x squared minus 16 divided by 16x times x minus 4. And at this point, we're about 70%, 75% of the total content covered for this problem. I say that because now up here, I've got an x squared. And anytime we see x squareds and we're simplifying usually means, can I factor? If I'm going to simplify, I'm going to find out, can I factor it? So part of simplifying is factoring. X squared minus 16, at this point in the semester, I would hope that you have looked at that and said, oh, that's the special form. Like the only special form that we've talked about is what's called a difference of squares. So difference of squares has been things like x squared minus 9, x squared minus 16, x squared minus 25, x squared minus 4. Those are all what we call difference of squares. So this would be x plus 5, x minus 5, x plus 4, so this is equal to x minus 4. Equals to x plus 3, x minus 3. And then x squared minus 4 is x plus 2, x minus 2. Down here I have x squared minus 16. Well, that's this one. It's the difference, subtraction, of squares. x squared and 4 squared. This is the difference of squares, x squared and 5 squared. X is squared, 3 is squared, and they're all differences. So the numerator here, we'll go down to another row, will be then x times x plus 4, x minus 4. In the denominator, 16x times x minus 4. So now I've combined all of my fraction into one fraction. And then I factored everything. Last step in factoring is there a 1 existing anywhere?
No.
What is x divided by x? 1. What is x minus 4 divided by x minus 4? 1. Again, now being careful here, it's because the x minus 4 is in parentheses, and down here the x minus 4 is in parentheses, because it's identical of parentheses, the whole parenthesis, that whole thing reduces. I say that because now what I have left, if I just want to clean this up a bit, in the numerator I still have this x plus 4, and in the denominator I have 16. The 4 is in parentheses. It cannot be reduced with the 16. That would be a mistake. The only way that this 16 could reduce is if there was also an even number in front of the x. If the even number, if it was like 2x, well then that's this and this are all divisible by 2, I could reduce it 2. Otherwise we cannot. At this point then that is fully reduced. This problem is complete. Then let's move on to, I believe, another review question. Yes. Same kind of thing. We're simplifying. Here we've got lots of fractions going on. Some are multiplying. Where's my pointer? Some are multiplying. One is dividing. All right. But with all of this, going to go with that same idea of let's factor. Is there anything either here, this one, well, this one is factored. How do I know that? There's just an x, there's just a 5. Can this be factored? Could this be factored? Can anything here be factored so that we can do some reducing while we do with the multiplying and dividing? Again, oh, look, it's a difference. Difference of what? Is this something squared? Yes. What's being squared? The x. The x is being squared. Is that something squared?
No.
Yes.
5 squared.
5 times 5 is 25. So it's a difference of squares. This is twice now in 2 slides that I've talked about difference of squares. So if you haven't yet identified this, you're making massive notes. Big star, triple underlined, bold, and highlighted in your notes. This must be important. We've talked about this literally every time in class since we've covered it. This would factor x minus 5, x plus 5. Sorry about that. All right. The denominator stays as x plus 5 squared if I want to. And I sometimes do this. I just do this. Squared means times itself, so I'm going to write the 2 together, just so I can see everything out there together. All right. I'll look at the next one. 3x plus 5. Sorry, x plus 15. 3x plus 15. Is 3x plus 15 factorable? Yes. What can you factor from each of them? 3. So when you do, it'll be 3 times plus 5. Factoring is division. Reverse distributive property. I've used a lot of phrases in that process. All right. Then I have this over here. Oh, but it's divided by, so I'll have to remember that when we get to that place. But can this be factored? I could just think, all right, are there two numbers that multiply to -10 that add to -3? Two numbers that multiply to -10 that add to -3. So you're thinking of all the numbers that multiply to 10. But then -10 means one's positive, one's negative. All right, so -5 times +2, well, that's -10. -5 plus 2, -3. So this would factor into x minus 5, x plus 2. Oop, I didn't need an extra set of parentheses there. So now I'm going to rewrite everything here. X minus 5, x plus 5. That's an ugly looking 5. That's better. It's multiplying, which means when you're multiplying fractions, I can just keep multiplying across. So times 3 times x plus 5. I'm going to pause for a second and not write anything else on the top. In the denominator, we've got these two items. So x plus 5 and x plus 5. And it's times 4x, which I could put right here. I'm going to put it out in front. I like to keep things without parentheses out in front. I know I didn't do that with the 3. And I said, let's pause there because now this is divided by. It's not multiplying. So I'm dividing by a fraction. What do we do when we divide by a fraction? Multiply by the reciprocal. So this will be times the reciprocal, which is going to be x over x minus 5, x plus 2. So now as one giant fraction in the numerator, and I'm going to reorder some, we're multiplying. We can reorder multiplying. And we know this because in your calculator, if you do 2 times 3 times 4, 4 times 3 times 2, they're the same number. So I'm going to reorder all the things that are being multiplied. So I'm going to have a 3 and an x out in front. Then I'm going to have an x plus 5. There's another x plus 5. And there's an x minus 5. X minus 5, x plus 5, x plus 5, the 3 and the x. There they all are. In the denominator, I have, the only thing outside the parentheses is the 4x. And then I have an x plus 5, an x plus 5. I have an x minus 5. And I have an x plus 2. There's an x plus 5, there's an x plus 5, there's those two. I have an x minus 5, an x minus 5, and x plus 2. And again, you're noticing I'm taking a lot of steps. Really keeping things separated out. Try not to do too much in any one step so I don't get confused. Last thing, when I'm multiplying and dividing, all this up here is multiplied. Each parenthesis set is multiplied. So each parenthesis set I need to think of as like a whole chunk. And then they're all dividing. So multiplying and dividing, I can reduce. X plus 5 over x plus 5 is 1. X plus 5 over x plus 5 is 1. X minus 5 over x minus 5 is 1. Is there anything else I can reduce? The x's. X divided by x is 1. I am left with 3. That's it in the numerator. In the denominator, I'm left with 4. x plus 2. And that is all I can reduce. I am done. So in that kind of a question, you're being assessed on, do you remember difference of squares? Do you remember greatest common factor? Do you remember how to factor a quadratic? Do you remember multiplying or dividing by a fractions, multiplying by reciprocal? Do I remember then that I can reduce? Lots of things that you can be assessed in one question like that. And now this one, we haven't done the Xbox method in a while, so I thought I'd throw this one on here as a reminder of what to do. So we're going to do this by solving. I know it's solving because there's an equal sign. A quadratic set equal to 0, which means I need to factor. So in the Xbox method, up here goes the 2x squared. That's the first term. The bottom is a times c, or the first term times the last term. And that's going to be negative 6. 2 times negative 3, that's negative 6. On the sides, I'm looking for two numbers that multiply to negative 6 and add to negative 1. And if you're like looking at that going, okay, the negative 6 I get. There it is, Professor, negative 6. Two numbers here that multiply to negative 6, but they have to add to negative 1. Because that number right there, that negative x, is actually negative 1x. So this is where you list all the numbers that multiply to negative 6. Negative 6, positive 1, 6, negative 1, negative 2, positive 3, 2, negative 3. Which pair multiplies to negative 6 and adds to negative 1? This set. So here, this would be 2x. This would be negative 3x. Where do the x's come from? Well, they have to add to negative 1x. So those two add to negative 1x. So that's the x part of the question. And then we do the box. Two x squared and negative 3. So this is always the first term. This then is the last term. And I have to put the negative 3x and the 2x in one of these two boxes. Does it matter which one? Sometimes it does, sometimes it doesn't. What do you think? So let's go ahead and try one of those. So if I put 3, let's see, if I do negative 3x here and positive 2x there, I already heard someone say it doesn't work because I'm looking at this and this. These two things have to multiply to 2x squared. If I do 2x and x, because 2x times x is 2x squared. 2x times what is 2x? Well, that's a 1. So that rectangle is 2x by 1. That gives me 2x. And then if I look at this column, say, all right, x times what is negative 3x? Negative 3. And then lastly, I check, does negative 3 times 1 equal negative 3? Yes. Again, we're looking at dimensions of that rectangle. That dimensions of that rectangle are negative 3 by 1, which is negative 3. This one, this box here, has dimensions of 2x and positive 1. All of these work. to give me all of this. All of this is this. It's 2x squared minus 3x plus 2x, that's minus 1x, and a negative 3, which means my factors are 2x minus 3 and x plus 1. It's now factored. And as was identified in the beginning, it equals 0. Ooh, stuff isn't showing up. So now I have factored out two things that multiply to give me 0. That's our whole purpose of solving quadratics, is to then say, well, if these two things multiply to 0, then either x plus 1 equals 0 or 2x minus 3 equals 0. Subtracted 1 from both sides there. Or here I'll add 3 to both sides, 2x equals 3. Divide by 2, x equals 3 halves. Those are the two values that if I took them and plugged them back into the original equation for x, if I would run them through as x, it would result in giving me a 0 as a number. So there's a quick review of the Xbox method for factoring and solving. So now new stuff. Logarithms. We talked a little bit the last couple times about what a logarithm is. A logarithm is nothing more than exponential form. Specifically with logarithms, on your calculator, you have a button that says log x. If you haven't looked at it, you can look at it right now. But if it's just written as log base 10, as log of x, it really means log base 10 of x. So if it just says log, the base is 10. It's a standard base number because we work in a base 10 number system. Tens, hundreds, thousands, like when you do decimals, tenths, hundreds, thousands, same kind of thing. If I had this, log of x equals y, and that's something you can graph. In exponential form, I would have to remember like, oh wait, that's right, my base here is 10. So if my base is 10, the order is base to exponent to equals. So it'd be 10 to the y power equals x. And that's, again, how we convert back and forth between logarithm and exponent. So if I have this, I have log of 10. Or realistically, I'm thinking, all right, well, this is log base 10 of 10 equals something. We'll call it a. What does it equal? Well, I'm going to convert. My base is 10, so it's going to be 10. Well, let me change colors there. It will be 10 to the a power. So 10 to the a equals 10. What does a equal? 1. Now, with your calculator, I want you to actually do this. Even if it's your phone calculator. All right. If you're working on a phone calculator, you're going to type 10 and then hit log of 10. First you type the number 10, then you hit the log 10, and then equals, and it tells you the number is 1. If you're using a standard scientific notation calculator, you type log, and then it gives you a parenthesis, and then you type 10. So then, for those of you that are working ahead, you looked at 10, or log of 0.01. Well, that one is, so this will be, again, and you don't have to do it necessarily like I'm doing, but I'm always thinking, this is log base 10. of 0.01. So that's going to be B. So now I'm thinking, all right, 10 to the B power. 10 to the B power equals 0.01. 0.01 is a decimal. It's also a fraction. Do you remember our units? After the decimal place, we have
100,000.
tenths,
Tens, 100,000.
hundredths. So I have 1/100th. So this is, I could rewrite this as 1/100th. Well, is 100 anything base 10? Yep. It's 1/10 squared. Because 10 squared is 100. Well, 10 squared is the same thing as 10 to the negative 2, if I have squared in the denominator. So when I do this, it should give me an answer of, if I do 10 of 0.01, my answer should be -2. Now, if you did 0.1 instead of 0.01, then you got -1 as an answer. But 0.01 is -2 because I'm 2 decimal places over. All right? And then shortcut on this one, is this 10 to a power? 10 to the third power. How do I know that? Well, there's 3 zeros, 10 times 10 times 10. So if I do this one, it should give me an answer of 3. Again, big part of this is make sure you grab your calculator, do it, see that you're getting the right answer so that on an exam or something like that, you're like, oh, yeah, I can use my calculator very effectively and efficiently to get that solved. All right, so now this is a quick little history, not necessarily relevant to you don't write this down, but just gives you an idea of what's going on. So Euler's number, E-U-L-E-R, is Euler. Euler is a mathematician. He didn't actually invent, or actually discover the number, I should say. It's not invented, it's discovered. He did not discover the number. Jacob Bernoulli did. Jacob Bernoulli was a guy who did a lot of probability, and in the process actually found some things that happen. And then it was Euler who realized the application of it has wide-ranging aspects, all right? Which means if I'm talking about investing, so finance uses E a lot. E, by the way, is this number, approximately, 2.71828.
I thought E equals MC squared.
That's a different E. E equals MC squared is energy. It's a different E. Yes. Yeah. And I'll be honest, I believe this E is more important than Einstein's E. Just saying. It's got a lot more application. But anyways, in finance, how much you have in your account after a certain amount of time is your principal, your initial amount, times E to the RT, where R is the rate and T is the time. And this is what would be what's called compounded continuously. And that's a process that they use in finance. They also found that like, oh, wait, things cool at a certain rate. So if you heat something up and then you set it down, depending on the substance, it will cool using the Euler constant, Euler's number, and whatever some constant is based on that. So the temperature after a certain amount of time is equal to the original temperature times E, which is a number, to the negative KT. T is time, negative K is based on whatever the aluminum cools off a lot faster than, say, cast iron. All right, so you cook with cast iron, your pot stays hot a long time. Cook with aluminum, pot cools off super fast. All right, and I don't know about you, back in the day when my mom would pack me a lunch to go somewhere, she was in a phase at one point of wrapping the soda in aluminum foil, which actually helps your can of soda get warm faster because aluminum is very quickly cools. So it's going to take the coolness actually from the can and dissipate it into the air faster. If you ever learned, you can actually take a piece of newspaper or magazine. If you wrap your soda in that, it'll stay colder longer. Paper is actually a very good insulator. They used to actually insulate homes with newspaper. They'd put the studs in, then they'd fill it with newspaper.
I I don't
Yeah,
have
and if you still go to some developing countries, if you ever go on mission trips,
Brick houses, let's go.
no, you go to these developing countries where it's like pallets. We've been down to Mexico, and they all the walls on all these homes, like we put together a couple of pastors' homes, like and they actually had like homes, like a building and everything. They found bags of concrete, poured their own floor, and then the walls were pallets that we screwed together, and then they would stuff the pallets with newspaper.
That must suck when it floods.
And then they would drywall it if they could find the drywall, or at least just put some sheathing up. And actually, you can keep it quite a few degrees cooler because at night it cools off. And then you just close it all up during the day.
If it floods though, that's
Yeah.
Very warm.
But anyways, so temperature is another thing that works. So finance, temperature. In chemistry, there's talking about half-life. But Euler's number, 718E, is where we get what's called the natural log. So the natural log is log base E. So it's really log base 2.71812 or something like that. I can't remember the number off the top of my head. I just wrote it down on the previous 71828. All right. And we would rewrite that though, instead of calling it log base E, we call it the natural log. And you're going to say, why is it ln if it's natural log? It has something to do with the Latin that it comes from. All right. But on your calculator, you have that button. You have ln. That means log base E. So now, use your calculator, find the natural log of 8. Do that now, but don't shout it out. So for me in my phone, I put the number 8, then I hit the ln button, and then at the top it shows me ln of 8, and then I hit enter. And what's the number that it gives you?
2.079441542.
Yep.
leave it like that.
And then leave it like that. Yep.
And
All right. And then what does this mean? So it's, again, how do we switch this between exponents and logarithms? This means, okay, so this is log base E of 8 equals that number. That means it's base E raised to the exponent of 2.079441542 is equal to, and this keeps going, equals 8. And that's something I want you to then type into your calculator because we're going to be using E as well. So go ahead and hit your E to the X, let's see, 2.079441542. Then hit the E to the X button, and it will show you E to that number. And E to the X is right above the natural log.
on the calculator, you press this.
Yeah, and it actually gives me 8.0000, like a whole bunch of zeros and a 3. All right, and again, it's rounding because this number goes on forever. But I mean, you get this like, oh, yep, that did equal 8. But because I had to round here, it's going to round there after like, what, 8 or 9 zeros? So then how does this work? If I did,
Is that where you leave it?
then you leave it like that, yeah.
Gotcha.
The 8 with all those number decimals and gets to, again, rounded, it's 8, yeah. So now, natural log of e to the third, you can just type that in your calculator if you want. First, to do this, if I type this into my calculator, I'd first type the 3 key, then I would type the E key, then I would type the natural log key. So if I did 3 E natural log, pardon? All together. In my phone, I would type 3, then I would hit the E to the X key, then I would hit the LN key, and it's going to tell you the number is 3. Natural log is log base E of e to the third equals some number x, converting from exponent to logarithm. That's my base, log base E. So it's going to be e to the x equals there, e to the x equals e to the 3, x equals 3. That's what your calculator just did. This one, it's going to be log base e of the, well, the 8th root is e to the 1/8 power. 8th root, 1/8 power. If this equals something, then I don't know what it is. It's going to be e to the y equals e to the 8th, y is 1/8. Again, just getting us in the process of seeing it over and over and over again. How do we go between logs and exponents? Exponents to logs.
Oh, Professor, can you go back?
So now, I'm not going to go back. So now, when we're doing this and saying, well, now I got to solve for x, and I have this in there, unless you look at this and say, oh, that's obviously, I can just, now remember, you can't divide a natural log away. This is not division going on here. This is function, the natural log of this number. So I can't do that. So I can't just get rid of the natural log, but I can rewrite it. Log base e of 3x equals 5. And then oftentimes, if it's a natural log and you're asked to solve, I'm probably going to be asking you to convert it to exponents. So I got to convert to an exponent. What is my base? My base is e. E. What's my power? Is it this or is it this? What's the process? E to the 5 equals 3x. And it's always that same process. Base, and what's on the other side? The equal sign of a logarithm is the exponent. Comes across there. Now, I've got e to the 5. E to the 5 is just a number. What is that number? It's 148.413 and a whole bunch more decimals. Equals 3x. So then what do?
You change it back.
Got to find x. How do I find x? Divide by 3. So then after you found that 148.413, you just leave that number in there and just hit divided by 3. X equals 49.471. All right. So that's one example of solving for x when we're using logarithms. In this case, we used the principle of, oh, I know that a logarithm is an exponent, so I'm going to convert to an exponent and then go from there. Another example is interest, where P is the amount of a loan. So there's my formula. And this is all the information. We're just going to verify the information by plugging it in the formula. Oh, the amount of the loan is well, my principal is 1,600. So P is 1,600, so I'm going to write 1,600. Times E, E is a number. E raised to the R, R is my rate. What is my rate? 9%. Got to convert it to a decimal. 0.09 times T, which is 5. So that'll be times 5. Equals A. So this should equal, when I do it, 2509.30. So on the right-hand side, oh, I got E to this number. First, I'm going to find 0.09 times 5. Do that in my calculator. Again, as we're doing this, now it's back to PERMDAS, right? Parentheses. 0.09 times 0.5. Run it through my calculator, that's 0.45. So I'm going to go e to the 0.45. So I'm going to leave that in my calculator and hit the e to the x button. So in my calculator, it will say e raised to the 0.45 power. Now I'll hit enter. Multiply that by 1,600. So this was 1,600. So when I did e to the 0.45 power, it gave me 1.568312185. And I never clear that out. I don't retype that in my calculator. Just leave it there and then go times 1600. 2509.29949. Since we're talking dollars, 299, that's why we rounded to 0.30. So again, all we're doing here is, did I use my calculator correctly? Those are the numbers. I'm feeling confident that I can plug things into a formula if I have to. So quick review, properties of exponents. Let's see, y to the a power times y to the r power is equal to y to the a plus r power. Same bases and multiply, the exponents add. X to the a over x to the r is equal to x to the a minus r power. When I have same bases, base x, to different powers, but I'm dividing, I subtract the exponents. If I have z to the third raised to the 2x power, this will be z to the 6x. When I have a power raised to a higher power, they multiply. 3 times 2x is 6x. Those are the powers, or the properties of exponents that we've done so far. Okay. Properties of logarithms are not a whole lot different, but now we're talking logarithms. Log of x plus log of y is the same as log of x times y. Sometimes we'll have this, and we'll convert it to this to solve. Sometimes I'll have this, and I'll separate it back out. But just like when we had exponents, same bases. Are these same bases? Yes, they are. Logarithms that are added can be combined to multiply. Same basis with exponents. When you had same basis as exponents and multiplied, we added the exponents. So again, logarithms and exponents, they're the same. You just got to think about them and then in reverse order. Which means if I have log base, and I'll use a number this time if you want, 3 minus log base of 2, that would be the rewritten together as log of 3 over 2. Because subtracting exponents meant we were dividing exponents. Same basis and divide, subtract exponents.
So how would you solve that with?
All right, and then our, why is it doing that? Go away. Our third property is this. Slightly different. So if I have log of 3 squared, this is the same as 2 times log of 3. And if you're wondering, like, well, why is that true? So the exponent actually comes out in front. We'll it's the powers of powers. When we have same bases and powers raised to powers, we multiply. And that's what the multiplying is, times 2. So whatever the exponent is comes out in front of that particular logarithm.
So how do you solve that, Professor?
So if I were going to put this in my calculator,
Yeah.
I would first do log of 3.
So
So I would type into my calculator 3, then I'd type log, then I would hit enter, and then I would do times 2.
so you work backwards all the time.
I would work backwards, yes.
So with log, you always work backwards.
You're going to work backwards, inside out, yeah. Yep.
Thank you.
All right, change of base. If I have two things and I don't know, so if I have log base 5 of 9, your calculator does not do log base 5. So if I had this, in order to figure out what that was equal to, I would do log of, so that's log base 10. I would do log of 9 divided by log of 5. And that would be how I would figure that out on a calculator. And again, these are all properties. And then we'll see how we use them here in a couple slides.
So would you put that into your calculator as 9 log divided by?
I do 9 log enter, and then divided by parentheses 5 log end parentheses. Yeah, that's how I would do it.
log, and
And I might be overkilling it when I do that on my calculator, but I really don't like to. So I do 9 log. Well, let's see if it would let me do, okay. Actually, so what I did in my calculator, I typed in the 9 key, then the log key, then the divided by key, then the 5 key, and then the log key again, and it actually shows me those numbers.
0.6989.
1.365.
9 log divided by 5.
5 log.
I did 0.69.
I'd have to look at it on your calculator. Oh, that's why all these calculators are a little bit different. So give me a minute and I'll take a look at it. All right, so then same thing here. That's all it is. Just showing the same change of base. That's how you do it. So now we're going to solve. I'm going to convert to exponent form. My base is e, because this is log base e. So e to the 0.18 power equals 3x. E to the this power equals 3x. Base to the exponent equals the value inside. This is calculator time. 0.18 e to the x for me. If you're doing it, this number should be 1.97217 and a bunch more equals 3x. And then to solve for x, it's 3 times. So we're going to divide both sides by 3. X equals 0.39907.
Would you round up to 0.04?
Nope, just leave it like that. Don't, if I tell you to round, round. Otherwise, don't round.
That's where the
Yeah, there's some standard systems where they say, well, you always round to this whatever. Like if you ever took calculus, AP calculus, their standard operating procedure is round everything to 3 decimal places. Doesn't matter. In stats, we say never round. In chemistry and physics, when you're actually doing stuff, especially chemistry, significant figures, which is a whole nother different ball of wax. So this, if, take a look at that. If the log base a of x is equal to the log base a of y, then don't say it out loud, but what do you think you could conclude in that statement? So take a look, think, don't say it out loud. If the log base a of x is equal to the log base a of y, what do you think you could conclude?
I wasn't gonna answer, but I guess
You're going to say what?
I was gonna have I had a completely different question.
Okay, but what do you think is going on here?
It's the same thing.
What's the same?
Log x and log y.
All right, well, they're equal to each other, but then what else could you conclude?
They're both one. Equal? I don't know. X equals y.
X equals y. So if the log of two things is the same, then those two things that were the log of something are the same. So if I can get everything to be the same log base, then all I have is whatever's left on the inside to solve. So then I have this. So when we start getting to here, now we're like, all right, how do we go about doing this? Well, I have two different logarithms, which is like saying I have two different exponents or two different, but they're all the same base. So if I can combine it into one thing, I can start having an equation that I can set up. So in this case, I have logs, and I'm subtracting. Logs and subtracting means I can combine those into one fraction. And that equals 2. So all I did is took these, I'm like, oh, subtracting same base logs. Subtracting means I'm dividing what's inside the 2. And now I have this. I can't take the log of variables. I can't do that, but I can convert this into an exponent form. Just log, written as just log, is base 10. So that means I will have 10. Which one's the power? The 2 equals x plus 2 over x. Well, this is 100 equals x plus 2 over x. Need to get rid of my fractions. I'm dividing by x, so if I multiply here by x and I multiply here by x, I will then have 100x equals x plus 2. These x's reduce. That was the design of it. Now I just have x's and numbers. Now I'm back to algebra. Solving for x, move all my variables to one side. Subtract x from both sides. 99x equals 2. Divide by 99. X equals 2 over 99. To be done on that one. All right. So that's one way. So taking some of our properties of logarithms, combine it into a single equation, then use the property of how logarithms are related to exponents to rewrite it as an exponential form. Similar idea, but what's different on this one than the last slide?
Not negative.
It's not negative, so I'm adding. So if I have logarithms that are both base 2, same bases and I'm multiplying, same bases and I'm adding, that means I'm going to multiply. So log base, go away camera. There we go. Log base, oh, come on. Well, that's why. Log base 2 of x times x minus 1 equals 1. Now I have a log. I have a base. I'm going to convert to exponent form. 2 is my base. What's the exponent? 1. It's always 2 to the other side of the equation power equals that number. 2 to this equals that. Equals x times x minus 1. 2 equals x squared minus x. It's a quadratic. Quadratics to solve, we set them equal to 0. Subtract 2 from both sides. And now I'm hopefully going to say, is there a way that I could do this the quick and simple way? And say, are there two numbers that multiply to -2 that add to -1? I mean, I'd rather not do the full x box or completing the square or the quadratic formula. But two numbers that multiply to -2 that add to -1. Always x and x to give me the x squared. One of them's positive, the other one's negative. That's the only way to multiply to a negative. -2 and +1 add to -1. Which means either this equals 0 or this equals 0. And the only way that happens, that first equation will be 0 if x equals -1. Second set of parentheses equals 0 if x equals +2. A little bit harder on this one. How long does it take an investment of $2,000 to double? So double means my amount at the end will not be $2,000, it will be $4,000. This equals P, which is the principal, which is my starting amount, which is $2,000, times 1 plus R is the rate, which in this case is 5%. R is in the numerator, 0.05. N is the number of times per year. So if it's compounded quarterly, how many quarters are in a year? 4, just like 4 in a dollar, 4 quarters in a dollar. Raised to the N, 4 times, well, the question asks how long, there's my variable t. So to solve for t, here's what we do. First, I'm going to simplify what's inside the parentheses. 4,000 equals 2,000 times 1 plus 0.05 divided by 4. This is 1.0125 raised to the 4t power. 4t is my variable's in the exponent. But I can still do some math. I can divide this side by 2,000 to get rid of the 2,000. I'll have 2 equals 1.0125 to the 4t. Make that look like a 2, not a z. Do we know how to solve exponents when the exponent's in the, or when my variable's in the exponent? I don't have an easy way to do that. It's not squaring, it's not square rooting. It's something else. So instead, this is when I convert from exponent into logarithm. What is my base? That's my base. So I'm going to convert this into log base 1.0125. What goes inside there? 2. The exponent, just like when we did exponents to logarithms, we did base to the exponent equals that number. Base to the exponent equals that number. All right, so these are equivalent. I don't know this funky, weird base, but I can change that to be log of 2 divided by log of 1.0125 equals 4t. So now, with our calculators, let's see if we can do this. And if you have to do it in chunks, that's fine. I'm going to take the log of 2. And that number is 0.301003. It's like 2,99999.
Yeah.
Let's leave it like that. In the denominator, I'm going to have log of, so I'm going to go 1.0125 log equals 0.005395. So that's that This is that. Now, let's divide those two. 0.30103 divided by 0.005395. And this fraction here simplifies to 55.79796. This equals 4 times t. Well, now it's algebra. So first thing first, put it in the equation. Simplify what was inside the parentheses. And then to solve for t, I work my way outside in like I always do. So divide, 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 divide. 2 equals that number. Convert it into a logarithm. And then recognize, well, I don't know how to do this, but these are just numbers. And I use the change of base formula. Find these numbers, plug in my... So now this equals 4t. Last step, divide by 4. T equals 13.949 or 95 if I say it around. And my unit is years. In just under 14 years, in an investment of $2,000 will double. And 5% is a pretty reasonable interest rate.
Is that like kind of normal?
So what's normal, it all depends. So normal depends on level of aggression in
Like your area?
in whatever you're choosing to invest in. So like a money market is going to give you usually like 4%. A CD, like say a 3-year or a 6-year or even like a 6-month, 9-month CD usually gives you about 5% in a good economic year. When you start doing investment funds, where you're actually like hiring someone to do it, they often can get in a typical year, which this year hasn't been so far. In a typical year, they will average out annually about 8 or 9%. Some years will be as high as 15, some years as low as 5, but then averaging out to that like 8 to 9 over a bunch of years. This quarter, our investments all went down just under 6%. So all of our investments dropped a bunch of money.
I know about that.
Yep. And then if the interest rate was 5.5%, it would just increase, that 0.5% in there actually does quite a bit. I think it drops it down to like 8 years. Maybe it's 9 years. Yeah, so a little bit of interest, but when it's compounded regularly, gets you there a whole lot faster. These are the check your understanding problems. Practicing a lot with using the properties of logarithms, converting from logarithmic to exponential. Those are the main ideas that we're doing with this.